In this problem, we have an assembly of 4 cables of equal strengths S. These cables are connected by 2 rings and they are supporting a weight W. Our task is twofold. First, for a given angle alpha, we have to figure out what is the maximum weight that can be supported by the cables. Second, we would like to optimize the angle alpha that for a given strength S, it carries the maximum weight W. We begin solving this problem by considering a sequence of free body diagrams. The first free body diagram involves the horizontal cable, the inclined cable, and the weight. We show the weight of the block and then tensions in the cables. T1 and T2 are acting along the cables. Next, we will consider the free body diagram involving the upper ring and the 3 cables attached to it. First, we recognize that the lower cable has already appeared in this free body diagram, and we denoted its tension by T2. What this means is that the parts of the cable where it was cut satisfy the third law, which means that the force T2 acting here is equal and opposite to the force T2 acting here, right? So I show this force in green to indicate that these two forces are related, or alternatively I can say the force T2 introduced in this free body diagram is not new. It has been already introduced in the first free body diagram. Then I show the forces in the cable T3 and the force T4. Now I can analyze these free body diagrams. I will start with the left one. And the equilibrium equations for this free body diagram involve some of the forces on X, some of the forces on Y, and some of the moments about the center of the ring is trivially equal to 0, simply because all forces have 0 arms. What this means is that the moment equilibrium equation is satisfied on one hand. On the other hand, it doesn't provide us with any useful information. Next, we can solve the first 2 equations and obtain the expressions for the forces T2 and T1. And I would like to pay your attention that T1 is equal to T2 cos alpha, and therefore T2 is larger than T1. The next free body diagram, again, I project the forces on X, project the forces on Y, and I'm not writing down the moment equilibrium equation because, like for the first case, sum of the moments is trivially equal to 0. Since I have already determined T2, I can solve these 2 equations for T3 and T4, and these are the answers. Please pay your attention that T3 is less than T4. That's point number 1. Point number 2, T3 must be positive in order for the cable to work. Therefore, the angle alpha has to be at least 45 degrees. if alpha is less than 45 degrees, then T3 is negative, and therefore this assembly is poorly designed. So I have determined that T4 is larger than T3, and now I would like to express T4 in terms of T2 because I need now to compare T4 and T2. It's not difficult to show, and I encourage you to do so, that this inequality holds, and therefore T4 larger than T2, T2 larger than T1, and T4 larger than T3. Therefore, the maximum force is T4, and its expression was obtained on the previous page. We can also simplify this expression. Just use the standard trigonometric identity sine square alpha plus cos square alpha equal to 1. Now I will say that the maximum load that the assembly can support can be found from the condition that the maximum tension is equal to S, the strength of the cable. And therefore, if I combine this expression and this expression, I will get that for a given angle alpha, the maximum weight that can be supported by assembly is equal to 2s sine square alpha cos alpha. Now let us optimize the weight with respect to the angle alpha. To do this, I will take the expression for W max and I'll differentiate it to find the derivative and set the derivative equal to 0. It is clear that this requires only to consider the expression sine square alpha cos alpha. Upon differentiation of this expression, I obtain this trigonometric equation. Upon dividing both parts by sine alpha, I obtained that the angle alpha should be such that its tangent must be equal to square root of 2, or alpha equal to arctan of square root of 2, which is approximately 55 degrees. Once this value of angle is substituted back to the equation for W max, we obtain a numerical value for W max, which is approximately 0.77 s.